Damien and I are going to talk about, so I'm Dave Landsman. I haven't been on the stage yet today, so I'm a standards guy at WD, and I've been in storage standards about 15 years, which in my estimation still makes me a newbie in storage standards. But in any case, so we're going to talk about command duration limits and improving this I/O density or IOPs per terabyte problem that we've been talking about quite a bit already this morning. I'm gonna talk about let's see. Yeah, so the problem we've discussed is I/O density, which we typically measured as IOPs per terabyte or megabytes per second per terabyte in other forms, a little more general term. It's a challenge as the capacity of hard drives grows. So as we see 32 and we get to HAMR and beyond HAMR, we're going to have hard drives higher and higher capacity, and as we were just discussing in the last talk, the I/O density problem gets worse and worse over time. And there's two general options to increase I/O density. You can increase the bandwidth of the device somehow. Either, in the past we had high RPM drives and we've had dual actuators, things like that, but we're not going to talk about any of that today. We could have many discussions and sessions on that. You can also approach the problem by improving the command efficiency with a better queuing protocol between the host and the device for scheduling commands. So that's what we're going to review, the model of CDL, and then Damien is going to share results that we've measured with the production version of Linux and real hardware. Okay, so the kind of where we stand today is that, historically, the hosts and applications have been limiting queue depth to very low numbers. And they're doing that so that they can achieve predictable latency, typically. And the result of that is you lose IOPs. The drive, you don't give the drive commands, it can't really do anything with them to optimize for rotational and seek latency. The other problem generally with priority schemes, when we talk about QoS, is that the priority schemes have typically been pretty vague. So you get things like real-time, best effort, background, high, medium, low, a numerical 1, 5, 10, but they kind of imply a latency, but they don't have any real. They're not based in time. So what we'd like to do, and what CDL attempts to do, is maximize IOPs while maintaining latency targets, and the way it really, for specified commands, and how it really does that is with deadline scheduling. So we want the application and the host to be able to put time into the equation when it receives commands. So this idea of deadline scheduling versus priority scheduling is pretty central. So deadline scheduling is central to CDL. So in the priority scheduling world, if we look on the left side of the slide, if we show here one command running in gray, and then these four new commands come in, and they're coded with high, medium, and low priority, just an example, and they get written to the drive. Or when the commands come up for execution, the drive, in this case, the drive is spinning, in the direction I show, and it's first gonna roll around to command 3. It's going to skip command 1, command 3, and it's going to execute command 4 first, and then it's going to pick up command 2 because it's the same priority as command 3. And so it goes, right? So it's using this priority scheme without really being aware of time or any direction from the host on time. It's just using the priority. With deadline scheduling, when the commands arrive, as you can see, they'll have windows of execution. Or when they need to be scheduled and how long, in windows in which they need to be run. So the host the drive can then build a command deadline list, And then when it goes to run the commands, you can see that what it does is it executes command 3 over here on the left of the spinning disk because it can. It believes, because it knows how long the high priority command can wait, it can safely execute command 3 before it does command 4. And so we get a different order through the commands in this case, and we end up with, and we still manage to maintain the latency of command 4, which is the high priority command. It executes within that red, the darker red bar. And then all 4 of the commands together end up taking a little less time than they would have otherwise. So this is the principle that we're trying to implement with CDL. In terms of the standard, or what it looks like, so the way it works is that the host provisions a device with CDL QoS requirements, i.e. duration limits. And the duration limits are expressed as time limits about phases of CDL commands. And those phases, I'll talk about them a little bit more, but there's active, inactive, and total phases in the life of a command. So you have time limits and you have time limit policies. And policies are really, they're associated with the various time limits. And they're really device directives on what happens if a time limit is exceeded. So the host provisions the device in these tables that you can see. There's, right now, the way CDL works is we have descriptors that contain these policies and time limits on the right. And there's up to seven read descriptors and up to 7 write descriptors. So the next thing that happens is the host starts sending commands that are CDL enabled, and it uses a 3-bit index in the IO command to select one of the descriptors that the drive already has in the device. And then the device can make seek optimizations and command retirement optimizations based upon the pre-provisioned limits, time limits and policies, and on which CDL descriptor was selected for the drive. So that's the basic operation of the spec. A little bit more on time limits. So what do they mean? So this is pretty important for the CDL model. So there's 3 time points that are relevant. So command acceptance, that's the time at which the device ingests the command. Command initiation is the time at which the device initiates actions to transfer or act upon data for the command. So I'll come back to that in a second. And then there's the time the command is completed. So that kind of fills out this picture at the bottom. And if you look at the intervals here, total time, inactive time, and active time, so inactive time is the time from when, inactive is when the time is ingested to when it's ready to be run. So that includes internal queuing in the device. It includes perhaps processing preparation for the reading CDL tables and stuff like the ones I showed to get ready. We don't account for that. We account for that in inactive time. Active time is when the command is starting to execute, and that includes the seek time because active time is defined as the device is executing a command, which means it's acting on the data for the command. Okay, so this is the basic time model, and then for each type of time, inactive, active, and total, we have time limit associated with each of those. So there's one other important nuance about the model, which is that time limits can be used, and this came up in our previous discussions. So time limits can be interpreted in different ways. So the host can, when the host provisions the drive with the descriptors, it can configure the time limits to be interpreted in one of 2 ways. So a time limit can be a scheduling guideline, which is really about a host direction on the relative importance of a command. And it can focus, these are focused on command scheduling as related to IOPs, or IO density as we commonly understand it. The other way a time limit can be used in CDL is as a command timeout. So once the command is in flight, it's been scheduled, it's run, but it's in flight, you may have, the host may want to say, stop processing this command because I've got another copy of it in another place. So don't do heroic efforts for error processing and stuff like that. That's fast fail. So that fast fail kind of was the first thing that engendered a CDL, as we heard in the last talk. But the command scheduling part of it, which is also in the model, is really important. And they're both important. And what we've tried to do is make sure that CDL can handle both command scheduling optimization and also this command retirement optimization. And so the last thing about the CDL model, I showed here we have an active time limit and we have an active time limit policy, right? So for each time limit we have a policy, right? And so these policies are influenced, the semantics of these policies are influenced by whether they're a scheduling guideline or whether they're a command timeout. And examples of, so the policy is what the drive does if a time limit is exceeded. And for schedule, in the scheduling category, the drive might say if the time limit has failed, time limit has been exceeded, then go execute the command at the earliest possible time after the limit expired. Or it might say go to the next CDL descriptor and use those policies. So there's a variety, there's 3 policies for that, and then there's 3 command timeout policies, and these are instrumented in the spec. And rather than talk about this in a lot of detail, I think it's better to let Damien talk through how we've used CDL and what results we've given. So we've shown that's the basic model of CDL. We've got time limits and we have time limits and time limit policies for when time limits are exceeded. The host can express a QoS for a command, for command scheduling purposes or for command retirement purposes. CDL 1.0 was published in ACS 5 and SPC 6. It was kind of the first instantiation. There's a new version of it. We're continuing, as we always do in standards bodies, to have debates about the semantics of fields in data structures. So we have a 2.0 coming, which is backward compatible, but it kind of it makes the semantics a bit more flexible. We've also not covered something that is also in ACS and SPC, which is sequestered commands, which we don't have time to get into today. But that's basically a way of creating a tiered queue in the device to hopefully encourage hosts to give more commands to devices and let them manage them. Okay, so now we're going to show some CDL based on upstream data. So take it away.
So Linux support of CDL. So let's start with an overview. As a background, to understand how we support CDL, you have to understand how Linux deals with I/O priorities. And there are 3 classes defined in the kernel, 3 classes of priorities that the kernel understands. Real-time, which is high priority, best effort, which is the default, and idle, which is the lowest priority level for background traffic. When an application wants to use I/O priorities, it can do that in 2 different ways. It can use a system call, which is I/O prior set, which will tell the kernel all the I/Os I'm going to issue from now on should be that priority level. Or it can do that also specifying I/O priority per I/O basis using the asynchronous I/O interface. The descriptor for an asynchronous I/O has this field called AIO rec prio, where you can set a particular priority for that I/O. And in the kernel, I/O priorities are essentially used only in one place, which is the block I/O scheduler. And the block I/O scheduler will make scheduling or ordering, execution ordering, or sorry, dispatching, command dispatching ordering decision based on I/O priorities. So this is the background. This has been around for decades. It's very old. And it comes back to the day when we had essentially ATA drive. I'm not talking SATA, I'm really talking ATA or IDE drives, who had a queue depth of 1, single command. So all the queuing was going on in the kernel. And when you wanted to control latency with that, you had to have something in the kernel that would tell which commands are urgent and which commands can wait. This is a very old technology. It's still there. But so what we did with CDL is we reused that interface because it's all existing, it's all wired already. But we added one field to the I/O priority definition, which is 16 bits as a value. We added, there were some bits unused in there, so we reuse those bits, and we can now place there what we call an I/O priority hint, which is going to be essentially contain the descriptor that the drive should be using for this command CDL limits. So CDL in Linux, it's all through I/O priority interface, meaning that you can apply a CDL limit to an I/O for a real-time, high-priority I/O, best effort one, or an idle one. You can combine also your CDL limits with I/O priorities. You will see that has important effect on what the end result is, because again, between your application and the drive, there is the kernel, and the kernel has to do the right thing if you want CDL to work correctly. Okay, so first of all, as Dave explained, you have to provision your CDL descriptor to the drive. We have tools for that. It's called CDL tools, not very fancy name, but it's upstream, it's on GitHub. You can download it, compile it. Very simple to use. You can look at what CDL descriptors are currently on your drive, change that, upload a new set of descriptors. It's all a very human-friendly interface. It's not showing you hexadecimal codes and you have to figure out what they mean. No, it's easily readable. You edit a text file to write new descriptor. We do the conversion, and that goes to drive. Very easy to use. We also have FIO modified to allow you to specify those I/O priority hints, which are going to be the CDL descriptors to use for I/O. So we added a few more options to FIO to allow you to define workloads that use CDL. And let's look at some examples. So what we did here with this set of results, you're going to see totally normal PC. We use a recent 26 terabyte SATA CMR drive. It could be SMR, works as well. It's just that the workloads on SMR are a bit trickier to generate. So for just make my life easier, I use a CMR drive. The kernel we use is the one that comes with Fedora 42, totally unmodified, out of the box, it works. So for the workload, I'm going to show most of the results are 128 kilobytes random reads. I'm going to show also a few with larger I/O, 1 megabyte, but essentially it's all random reads here that I'm going to show. I'm going to show examples of CDL using a kind of a best effort policy. So meaning that if the limit, the CDL limit for the I/O is missed, you're not going to see an abort. And I'm also going to show examples of fast fail policies which abort I/Os. And so the results, I'm going to show IOPs and the 99th percentile tail latency that FIO measures. And starting with the baseline, so meaning what happens if you use a drive with no CDL. So This is essentially doing 128K random reads at varying queue depths up to 64. So remember, it's a SATA drive. Max queue depth on SATA is 32. If you go beyond 32, you get queuing on the host, meaning that the left side of this picture, the left side of the dotted line, it's the drive working. If you go on the right side, it's the drive plus the kernel. Important again, you'll see some results. That's why if you look at the right side plot here, which is the latency, the left side is the IOPs, you don't see much increase going beyond 32 queue depths for the IOPs because, well, you're already maxing out the drive. But you do see very much different tail latencies if you go beyond the max queue depths because you are now subject to what the kernel does with your I/O and what ordering, what dispatch ordering it does. And so depending on if you're using a scheduler or not, you see the dotted line is using a scheduler. The scheduler is trying to optimize for IOPs, but of course it's failing. You're already at the maximum, so your tail latency gets a huge hit. So that's what you may see depending on your drive usage here. So this is the baseline. Everything I'm going to show you, I will also add the baseline to the plot so that you can compare how CDL changes all that. So the first example here, we're going to take 20% of IOs with 100 millisecond limit. And the limit here is a scheduling limit. It's not a fast fail limit. Here you go. See the latency? Your 20% of I/O, they are getting 100 millisecond tail latency, 99th percentile tail latency. If you look at the IOPs, the blue line is your baseline, so that's the maximum that the drive can do. With that workload using CDL, your maximum IOPs is actually now the red line underneath that. So there is a drop in the maximum IOPs. There's no free lunch. Those 100 millisecond tail latency control, that doesn't come for free. So we're trading some IOPs for that latency control. So this is really the point about CDL. And so the title of the presentation says, Improving IOPs with CDL. Well, I'm not trying to contradict the title here. Remember, the point here is that CDL allows you to use your drive at high queue depths while maintaining latency, which is not something that was done a lot until now. And you still get much, much better IOPs compared to a solution where you do latency control based on queue depth control. So this is the entire point. What if you keep increasing your queue depths here, you go beyond the 32 max of the drive? Well, then you hit the problem that the kernel doesn't understand CDL. It just passes that information along to the drive. So now your queuing on the host side kills you, and you see the tail latency increasing again because the block IO scheduler will not schedule your short time CDL limited commands before the other ones that don't have a limit. How you solve this? Remember, a CDL is a hint to an IO priority, so you can now, those 100 millisecond limited command, if you issue them with a high priority, they go first, and you maintain your 100 millisecond tail latency that you want. So even going further beyond what the drive can do, higher queue depths, you can still maintain your target tail latency by also combining CDL with IO priorities that the scheduler understands. So this is the basic example here of CDL. That works also, so that was 128K random read. That works as well with much larger command here, 1 megabyte. The drive adjusts its internal scheduling based on the size of the command. It's not something that is fixed for some size. So it's all dynamic, and you still can maintain that 100 millisecond tail latency even for larger command. Within reason, of course, if you try to do that with super, super short limits, of course, the drive needs some time to transfer a much larger command. So the limit you use for your workload has to to be consistent with the I/O size you're receiving. Another example where this time two classes of IOs were seeing 10% with 100 millisecond limit, 20% with 300 millisecond limit. And again, we make the target. Same pattern as before, you trade some IOPs from the baseline for that tail latency control. And again, if you look at the 99th percentile tail latency here, we see our two classes, 100 millisecond, 200 millisecond being there. You'll also notice that the tail latency of commands that don't have a limit is actually better compared to the baseline. That's because of the optimization in the scheduling within the drive pick up commands that don't have a limit as it goes, because it knows it can do them. And overall, you can actually also, CDL also improves the tail latency for commands that don't have a limit. Instead of doing a blind aging management of commands that are queued, it picks them as it goes because it knows it can do them. And that improves tail latency for all commands, not just the time-limited one. Okay, another interesting example, which is fast fail. In this example, so I'm pushing the limit really kind of in unreasonable, not very reasonable territory here with 50 millisecond inactive time limit. So the inactive time limit is the limit of time for how long the command may stay queued in the drive without starting execution. And 20% of commands are issued like this. And we also put a 50 millisecond duration guideline limit on, so total time limit on the command, meaning that we want that command to be completed within 50 milliseconds. And we don't allow it to stay inactive for that amount of time. So it has to be processed. That's essentially what the workload is saying here. So there was Rick mentioned that in the first presentation this morning, but when do you want to actually use fast fail and have your command aborted without being processed and getting back an error? If you're using a single drive to store files, you definitely don't want to do that, because it means that your workload is going to fail. You're going to get I/O errors. When is fast fail useful is when your application is actually using multiple drives to access some piece of data that is distributed between those drives. In that case, the latency you're going to see for that user I/O is going to be dependent on the slowest of those drives. And so fast fail is a way of limiting the latency of that user I/O, which is distributed between multiple drives, assuming that you have a way to reconstruct the data that you're going to be missing if you abort one I/O. Distributed object store is the typical use case here. So there are two cases here for fast fail. One is policy D. The other one is policy F, and I should have reversed that because policy F is easier to understand for SATA. It's a hard error, NCQ error, which is going to, because of the SATA error model, it's going to abort the drive queue, so all the commands get aborted and you resend the one that are not an error, and the one that was aborted due to the CDL limit, you get back an error. Policy D is a way to avoid that queue stall that comes with NCQ errors. And you get back actually a success status for that command. But there's a bit that says sense data available, and you need to go and ask the drive, read a log that tells you the sense data associated with that command, which is going to tell you if that command succeeded or actually was aborted due to a CDL limit being exceeded. It's a very complex kind of completion processing you need to do, but it avoids the queue stall that comes with NCQ command errors. So, policy F, NCQ error. The workload I specified is actually impossible for the drive. 100% of the time you're going to get aborts. So that's what I'm showing here. So the interesting thing to look at is the 99th percentile latency, the plot on the right side. And you see at the beginning, it's actually maintaining up to Q depths of 16 or so. It's maintaining the 50 millisecond, but as you push forward the Q depths, the drive really can't keep up, and it's going to start aborting commands because it cannot make it on time, and it aborts commands. It sends them back to you with an error, and that error processing causes the drive Q stall and all the error handling on the kernel side, which results in your tail latency to actually increase. Bad, not what we want. We want to cleanly abort commands without the Q stall and don't see this kind of increased tail latency. So, second solution, policy D, which is not supposed to, which is not generating NCQ abort, but to know if that command was actually aborted or not, you need to go read that log page that tells you the sense that are associated with the command on completion. That's more work. Your tail latency still increases. Because the ATA maintainer, I'm not going to say who that is, was lazy and used a non-NCQ command to go read that log, which causes a Q stall. We're back to square one. So yes, same problem again. But the ATA maintainer, again, I'm not going to say who that is, did some more work and he fixed this. So this is all solved. You get your fast fail with your 50 millisecond tail latency being maintained. All good. Not upstream yet. I'm the ATA maintainer. I need to clean up the patches, send them, approve my own patches, put them upstream and in the kernel. It's coming. So this is, by the way, the drive I forgot to mention. That's connected to a SATA port here, HCI, so it's not involving any SAS HBA firmware, which may or may not do the same thing. I am not going to comment there. I have not actually really looked in details what they do. But fast fail, it works. You can still maintain that allows you to, even a crazy workload like I have here, you can maintain your latency control. If you look at the IOPs, you'll see there's a bit of variation and you actually get better IOPs, which is counterintuitive, but you do improve the IOPs by aborting some commands. And you can maintain your tail latency. And I think, well, what, one more? No, we are, the last one is the conclusion.
Okay,
yes. Any question? Yes?
In the absence of CDL, the firmware is always provided some degree of fairness.
Yes. So there is some command edging going on so that you don't see crazy tail latency for your commands when you're running at high Q depths. So there is that exists. Yes, there is some. The problem is that the some makes some not happy and others are okay with it, others not. And so as a drive vendor, we always end up, I'm pretty sure other vendors do the same, but having different versions of a particular firmware with tweaks for that particular customer because they want to see different behavior. So CDL is a way to avoid that, to have something much more flexible that doesn't depend on the firmware update. It allows you to control the tail latency you're going to see from the drive without having to change the firmware.
And there was only one. So, one limit that was coded in to the firmware as David mentioned. But the CDL allows multiple classes of commands now. So
yes.
It's programmable by the host.
So kind
yes.
of related to this what you just said. So first of all, so these policies, they can be defined and they are stored inside of the device, yes? The policies definition. Yes.
Yes.
So then you can address them kind of dynamically, because flexibly you can define policy for now, because they're not hard-coded. I define them, right? I send them to the device, and then I just use them with the command, address them. Did I get it correctly?
So a CDL limit, so it's as Dave described, so 3 different time limits
Exactly.
and 3 policies, one for each limit, that tells the drive what to do if the limit is exceeded. So that's one set, and that's called a CDL descriptor. So one IO will point to one CDL descriptor.
Exactly.
Yeah.
But I can define these 3 policies by my as a.
No, so you have a choice. The policies are already defined by the standard. It's not unlimited. There is this, and this. So you pick which one you want.
Yeah, we have a set of code points in the standard
Yes.
that define specific policies that you can select from. We could add more. You know, it's not, but it's not defined, the policies are not defined
But
by
there's 7
the
descriptors that
application.
you can use.
Exactly.
7 classes of
7 reads, 7 writes. Yeah.
Okay. So another thing which I wanted to note, so you said that the standard to 0 is compatible backward, because I think I noticed you use the different codes, right, of the bits, so that's why it's compatible.
So,
Just,
let's go back to that,
extend
the policy slide.
Yeah, here, right?
Yeah,
It's
so,
like 0, 1, 2, and this 4, 3, 5.
so this is, I probably shouldn't have put this in because it'll rat hole us if we go into it, but for completeness, I wanted to add it. I mean, so in the first version of CDL, we had a certain set of code points. And in the second set of CDL, in the second version, we actually obsoleted 0 and
1 and then 2.
And we repurposed them. You can still use the old ones if you want, but so that's why I don't want a rat hole on it. But they mean the same thing, but we just swapped opcodes.
Yeah,
a little
exactly,
bit.
because if you obsolete them, it's kind of nine for the CDL 3.0 to reuse this, what was, right, as the
Yeah,
idea,
yeah,
right?
yeah.
I guess.
So, 0, 1, and 2 were mainly obsolete because there was diverging implementation between manufacturers. Right? And we created 3, 4, and 5 to have better alignment so that when you buy a D drive and a CDL product and a Toshiba drive, you do the same thing.
Yes,
These policies,
yes.
which
Yes.
wasn't the case with policy 0, 1.
Yes.
In the beginning. Okay, thank you.
So are policies 0, 1, and 2 going to be deprecated?
They are.
Well, no.
Well, they're obsolete. They're not deprecated because the drive vendor is still free to implement them if they want.
We could deprecate them, but so far they've been obsoleted, which means they're still in the old standard. And if someone wants to,
Which is a problem, right?
I mean, you're gonna, you know what version.
Other ecosystem partners have a problem.
We can fix it if we need to, but people know what version of the spec they're supporting, so.
I think from a standards perspective, okay, you make it obsolete because they're a host, they're going to issue it to you for some period of time. Maybe a long period of time, right? But you don't want people to go continue using them. And when you've got diverging implementations, what that means is the customer becomes the place where they come together. And they don't come together the same for each customer, right? So we're encouraging people to use 3, 4, and 5, but if you've already implemented it and you're running it, okay, we're not going to turn around.
So remember though, over the wire, the only thing that flies are the 3 bits for the CDL descriptor index.
Yeah.
Those values are in the CDL descriptor in that log page. That's it. So at runtime, there's actually no difference between one or the other.
Well, at runtime, there's very differences between one and the other.
Well, the drive will behave differently, but at least the way the commands are sent and then the completion doesn't change.
Agreed.
So what I love about this, that now as a person which is developing distributed file system much high level, when we have thousands of drives, right? Because we were doing it on high level, we're doing that. We were trying to, of course, query it somewhere, and if server is slower, we just say fail because we have data from somewhere else. But we could not tell the hard drive itself fail too, right? It will still continue maybe doing this job, and now we can go to the bottom, to the device, and already prep them. But I have, is it working for writes also, right? I can cancel the
So,
or not.
okay.
Especially in the SMR, like
It's
the zone.
so for writes a bit more tricky because the drive has a write cache normally. So it depends if you have that on or off.
Yeah, true.
Because if you have write caching on and your write command goes to the cache and you get a completion immediately, you don't actually have the data persisted, and so your CDL limit on that is kind of meaningless.
I was kind of hoping that I can invalidate the cache which is not yet committed to actually to be on the memory. So I thought I already made the write somewhere else. Stop writing. Yes, give me resources back as a drive. They don't, right? Just to inform the drive cache, which already say, oh, I just finished writing because I have my write cache, as you said, with optimality is even safe, right, to do it. But let's say my high-level host level software knows that we already have it somewhere else. Don't push it from the cache for them. Is it?
So if you fail to write,
Yes, exactly.
the system wants to maintain the same redundancy. So
The system.
if the system level on the erasure coding. So
Yes.
the system needs to find out that the write didn't actually occur, which is very rare because the drive has other means of writing it in different locations, some spare locations. Well, let's say it didn't fail. The system needs to know that because it wants
Yes.
to maintain the same redundancies. It has to write that same thing somewhere else to get that same redundancy.
I was thinking that the system is more eager, let's say, in doing this writes. Let's say if you have error coding, let's say 5 plus 3, we do 5 plus 4 on purpose, right? We do one more because we want to see which actually really first finish and to tell others, by the way, we already have it somewhere else, remove it. Yes? So even if you have kind of for confirmation, one of them would like to also inform that we don't need you, yes? And maybe we are fast enough that the cache will not start populating the data during the write.
So one thing you have to give us, okay,
Yes.
is to not decide a drive has failed and removed it because it got a write failure. Today, if we fail a write, you get very upset on the host side. You don't like failed writes,
Yeah,
right?
sure.
So if we're gonna go ahead and say this is the active time for a write, and you want to get rid of retries or whatever it is you're trying to do, your first target of opportunity is just to do something to limit retries. But your second is to limit your active time, and that causes write failures for sure. And then you can't say the drive is getting write failures, okay, right? We need to replace it now because write failures show up and say your smart statistics.
Or you start depopping head or something.
We will, yes.
There are dragons here.
So on writes, you're also, there's the temporary reliability and your permanent reliability. So on a write, you're gonna try to, if you have 20 pieces to write and you're good on the S3 write at 15 from a temporary reliability, you let the other 5 trickle and close out to get to your permanent reliability at 11.9. So those are a lot of decisions on writes, but you're always wanting to write 20. Writing 19
Yes, it's true. And I just want to inform this extra.
We have one.
Yeah, there's two in the.
Yeah, sure.
Two gentlemen have been raising their hands for a while, so.
Go ahead.
So question, how do you expect which software layer is mostly to be involved in generation these descriptors and classes, and then which software layer is mostly to generate hints about particular IOs? Is it to be in that, for example, distributed file system layer, or it is just to be that burden on an application side?
So, distributed file system is an application side thing. There's no distributed object store in the kernel. So all what the current interface does is really the wiring between application and the device to pass on the. Yes, Christoph, I know. I'm talking about it currently.
Because the entity that needs to be in control, if you're using a file system, kernel file system is the file system. And it's different if you have an application like a distributed file system built on raw block device or pass-through, in which case you can do whatever you want, obviously. for anything that sits on the local file system, the local file system is the one that
And that's something we need to wire because we don't have that yet.
And here's the question, for instance, for SMR, how we can do it, like use this particular policy? Or even
Same thing. But even more challenges with writes, that's all. Just be careful about that one.
Okay.
Okay,
Yeah,
go
so,
ahead.
what are the semantics of write caching with respect to CDL? Does it apply to the initial write and response only, or to the permanence of the write?
I don't think the standard says anything about that.
It does not.
I encourage you,
It does not.
but I don't think there is anything.
When it comes to write caching, the standard does not say permanence. Okay, there's nothing there. Once the device has accepted the data, it's in the device, right? And what you're waiting for is command completion. And so CDL is all about command completion, getting to a quicker command completion. So if your write cache is on and you've accepted the data, we will report command completion. Now, if you have, say, an active time that allows you to cache but not to write the media, which is very doable.
Yes, very doable.
Very common middle ground there. You could do that. And then make all uncached writes in a write caching environment fail. Now, I don't think you want to do that. But the standard doesn't tell you how to do it. That is basically a technology that's there, works in a certain way. And so you can do that if you want, but the standard doesn't tell you how to do that.
Question.
Yes. Last one, probably. Yes. I don't know who was first.
You had a slide about deadline scheduling that got me thinking. You said a lot of systems wanted the queue depth to control latency. Will increasing the hard drive queue size become particularly useful at some point?
I would love to, but SATA is unfortunately limited to 32, and that's probably going to be like that forever. So all of that discussion, by the way, works on SAS as well. So SAS drives.
What happens to NVMe?
We will need a slightly different model, but we think that essentially roughly the same concept will apply.
Well, actually, NVMe would work even better there if NVMe does it the way I think it should.
Which is?
With NVMe, you've got multiple queues, so you can put your different priority levels in different queues, and you don't even have that head of queue problem with a lot of the higher latency, longer completion time commands blocking the important low latency ones. So this means we'll actually get NVMe HDDs.
Yeah, the problem there, I'm working on that problem. And the problem is the number of queues you have to support in an NVMe hard drive starts to become hardware expensive. Right?
Well,
The good thing is many of them don't have to be huge, and NVMe has a concept of limiting the total number of outstanding commands overall queues now. It's actually, I think right now it's a pain that we need to make it a hard limit, because that way you can say, I support this many outstanding commands, but you can't configure it into multiple queues or not, because you don't want to get that ballooning number of a lot of queues and a lot of commands per.
I mean, I'm sitting here looking at, okay, I've got, 7 priorities today in the standard hard drive. There's 7 queues. I go to NVMe, I've got 7 slots, but each one of those 7 can be programmed for things, right? So now
It's him next, so.
Going to different processors or going to the same processor, who's to say, and that configuration just by itself, even if you limit the size, ends up starting to get costly.
Hey guys, we are at time.
It's hallway time.